Last time we finished by talking about effectively closed sets, and we were about ready to start talking about the effective compactness theorem. Right? And just like if you look at the book for the compactness theorem, there's a whole list of different properties, all of which are called the compactness theorem. Here there will be a couple of properties. I seem to have four properties which in some sense are closely related to the compactness theorem. So we start by looking at a T, a subtree of the full binary tree, which is computable. Right, and then we know a lot of things about the situation already. If we now look at the set of infinite branches through this tree, then that's exactly what we called an effectively closed set, and we also observed that there was not an entirely random name. This was a reasonable kind of thing, because every closed set is obtained as the set of infinite branches through some tree, and then the extra effectiveness we get is that our tree is computable. And we also noticed that if you take the complement of this T in this set of sequences of finite sequences of zeros and ones, then you exactly get a collection of basic open sets that unions up to the complement of this closed set. So these observations are nice because it shows that these trees, which are clearly combinatorial objects, are well behaved with the topology, and so these combinatorics can tell us things about the topology. The first observation we make here is that if we look at a particular subset of this tree called Tx, X is for extendable, this is the set of extendable nodes, so this is the set of those sigma in T such that, let me use the same definition as in the book, there exists an F which extends sigma such that F is an infinite branch through the tree. Right? So these are those nodes which can be extended through to an infinite branch through the whole tree. And then we notice that this is a pi01 set. Right? What meant pi01 set? Pi01 set means it is described using a single universal quantifier over something which is computable. So how do you describe this set as a pi01 set? The way we wrote it down, it's a sigma 1,1 set. Right? There's an existential quantifier, that's the bottom one, but this existential quantifier is a quantifier over the reals, because it's an infinite branch, that's the upper one. So the definition is not pi01, but being extendable using the ideas in the proof of Koenig's theorem, or lemma, I forget what we call it, the thing named after Koenig. You notice that you are extendable if and only if at every level longer than you there exists a finite extension of you to that level. So what this means is that you look at this set, computable set T sigma, the collection of nodes which extend sigma, and you need to see that this is infinite, which means for every natural number n there exists a node at that level. And now, superficially, it sounds like I gave you a pi2 formula, but the second quantifier, there exists a node at that level, is a node over a finite set. So it's really a computable thing to check. Therefore, this whole thing is pi01. Instead of extendable nodes, it's pi01. from this you get, right, if this set is pi 0, 1, then its complement is sigma 0, 1. Sigma 0, 1 sets are nice because we know that being sigma 0, 1 means you many 1 or 1, 1 reduce to the halting problem. And if you reduce like this to the halting problem, then your complement, right, it doesn't necessarily reduce the same way. But what do you need to do for a complement? Well, you just need to flip the answer. Therefore, the complement of Tx reducing to 0 jump implies that Tx itself Turing reduces to 0 jump. Okay. Item number 2. If there are infinite branches through this tree, now of course, if T is not computable, T is just an arbitrary tree, then you can get very complicated sets of infinite branches. Any closed set, after all, and closed sets can be, in some sense, closed sets are simple, but in other senses, closed sets are complicated. But here we have a computable tree, and from that fact, and if this is non-empty, you can wonder, okay, it is effectively open. How good or bad are its members? Some of the members in this set can be extraordinarily bad, complicated, hard to describe. But if you have an effectively closed set, then it contains a member which is reducible to 0 jump. Right? Effectively closed sets can contain lots of very complicated sets, but they contain at least one thing which is reducible to 0 jump. And of course, this I think if you understood one, then this hardly surprises you. One says that you can decide using 0 jump which nodes are extendable. Then again, by a similar proof as used for Koenig's lemma, you can say, okay, so this is non-empty, therefore at least the root node is extendable. According to this definition, like there is some sign. The root node is extendable. Look at both extensions of the root node. At least one of them is extendable, and asking the oracle 0 jump suffices to figure out which of the two is extendable. And therefore, using 0 jump, you can compute longer and longer initial segments of f. Therefore, f is computable from 0 jump. Right? You need to make sure that you pick a preference for going left as opposed to going right, so that you do the same thing always for different lengths, but then you're computable from 0 jump. And then you could wonder very quickly, okay, so this theorem, or this part of the theorem I introduced as effectively closed sets contain members which are not too bad, right, computable from 0 jump. Can you get all the way down to every effectively closed set contains a computable member? That would be nice. So let me give a faulty proof for why this is not the case. And then later I'll give a real proof. The faulty proof is that, well, right, if I could find a computable member, then I find this computable member using the T as the oracle, which is not really using T at all because T is computable, so you don't need to use T. But if you had this expression, then you could say, well, right, for computing f, you're asking some questions of your oracle, of the tree, and how much do you get to ask from the tree? Well, for any part of f, only finitely much information. Right? So your finitely many oracle questions ask about some nodes that are in the tree. And then you build this initial segment from it. Well, you can now change the tree by keeping it the same on these oracle questions, but cutting off everything which extends your current approximation to the f. And then you defeat the strategy. Right? It almost seems like a proof. This phi, it can only ask finitely many questions before it decides whether you go left or right on the first branch. And then as soon as you decide to go left, you change the tree so that the choice was wrong. It's a common strategy that often works. In this case, it doesn't really work, because this phi, instead of asking t oracle questions, it could use the index of t. Right? T is computable, therefore it has an index. And if I change the tree, certainly the index would change. So this is not quite a proof, but it is something of an argument in the direction that doesn't work here, but it works in other places. Therefore, I figured I'd put it forward. Nonetheless, it is true that not every effectively closed set contains a computable member, but not via this proof. We need a different proof. But it is a nice strategy, this one I suggested here. You change the oracle where the computation isn't looking, and then suddenly it became wrong. Okay. 3. If f in this tree T is isolated, then f is computable. Right? But what does it mean, isolated? Something in a topological space is isolated if there exists an open set which contains only this member. Equivalently, of course, you're isolated if there exists a basic open set which only contains this member. Now, that's kind of nice, because we here in this full binary tree, we have our infinite branch f. And this infinite branch f is presumed to be isolated. What does it mean? Well, there exists a basic open set. Right? It looks like a cone like this. A basic open set consists of all things that start with a given finite sequence. So there is this basic open set such that the only infinite branch to the tree in this cone is f. And now the claim is that from this f is computable. Okay, how do you do this? Well, you are here at the first level, and you have to wonder again, right? I'm computable, or sort of the key step is to figure out the first choice. After you figure out the first choice, you do the same thing for the second choice, right? Going left or right. So, going left or right, well, only one of these two is an extendable node. Because otherwise this wouldn't be the isolating basic open neighborhood. So only one of these two is an extendable node. What does it mean? Well, for the other one, there exists a level, maybe extraordinarily long, but it doesn't matter, we're not trying to be quick about it. There exists a level such that this node has no extension up to that level. And so this is something you can search for. You're wondering, am I going to go left or right here? For both of these things, you keep checking longer and longer levels to see if there are extensions. And because you know the node is isolated, at some point above one of these nodes, you're going to find it has no extensions. And then that node was the wrong choice, so you make the other choice, and then you iterate above there. So that's how you get from isolated to computable.
But of course, finding the isolating set is, you have to Given the isolated set.
Yeah, if you're given, you're given, I guess if you know it's isolated, you can find the isolating set as well by the same strategy. But if you don't know it's isolated, you can't decide. That's a very complicated question to design isolation. Okay, then the last part of this so-called effective compactness theorem, which most looks like an actual effective compactness theorem, says that if we have an open cover A, and now I'm using the book notation, right? A is a set of finite sequences of zeros and ones, then this double square bracket of A is the union of all the open sets determined by these finite sequences. So if I have such a set which covers, and A is not too bad. A is a computably enumerable set, right? I can enumerate these things. Then there exists an F subset of A which is finite such that this already covers. Now this is of course not the effective version, it's just the compactness theorem. I guess it's the compactness theorem with an extra hypothesis. But the statement is, and we can effectively find a canonical index for F. Right? If you have the CE set which covers, and again, deciding whether a CE set covers is a very complicated question, but if you're given that you have a CE set that is covered, then it's easy to find the finite set, or find a finite set that also covers. Now, in order to figure this out, the first observation you make is that if I give you a finite set, it is really easy to decide if it's a covering finite set. Because if you have finitely many sigma, you just check if these finitely many sigma cover, right, an initial segment of the tree. You just check, is it the case that every real starts with one of those? Now it sounds very complicated. For every real something happens, but it's just a finite combinatorial check on these finitely many sequences. So if I give you a finite set, it's very easy to check if it covers. So now this part of the theorem has become easy. You start enumerating A, which you can because it's a computably enumerable set. Every time you enumerate a new element into A, you check, did I just reach a finite set which covers? If yes, you're done. If no, you continue. And because, by the ordinary compactness theorem, you know at some point such an F will appear, this computation stops and you will find the finite set which covers. Good. Everybody happy with it? Okay then. Then now I'm gonna show two theorems which get pretty close to completely answering this question 2 here. Well, it wasn't a question, this theorem 2 said if you have an effectively closed set, then it contains a member which is not too bad, it's Turing reducible to zero jump. Then I incorrectly argued that there are no computable, that there are not always computable members. Obviously there are closed sets with computable members, but there are not always computable members. So here comes the real proof of that fact. that there are not always computable members, and after we have proved that there are not always computable members, we will prove that there are always low members. Right? And low, remember, is a class bigger than computable, but it's those members which are useless as an oracle for the holding problem. Right? The jump of a low set is exactly the holding problem. So they are the things which, at least with some intuition, are pretty close to computable, even though they aren't. Okay, so first, there are no computable members. Well, for this, just observe that if I have WE, WI, two CE sets, then I can look at this class, the class of those sets S, such that WE is a subset of S, and WI is disjoint from S. Right? These S are exactly, if I have here WE and WI, these S are exactly the sets that separate these two CE sets. So this is the class of separating sets. Now, of course, it looks like a class of subsets of the natural numbers, but if you look at it the right way, it's really a set of characteristic functions, and therefore a subset of 2 to the omega. And now we will see that this is really a pi01 class. Right? What's a pi01 class? A pi01 class is an effectively closed set. It's a set which is given by one natural number universal quantifier over something computable, or right? the type of things we've been studying. So, and this happens to be easy to see with everything we've done so far. Right? Which S do this? Well, those S that completely miss WE, no, that completely hit WE and miss WI. So, not being such an S is easy to see. You're not such an S if there is something in WE which is not a member of you, or if there exists something in WI which is a member of you. And both of these statements amount to certain computations converging. But computations converging is too complicated to give a computable tree. Now we have a standard solution for this. Maybe it's slightly premature to call it standard. We've at least used it once before. It certainly is the second time, if not the third time. The standard solution for this was, okay, this is about computations converging, but we're looking at nodes in a tree, and so instead of just these computations converging, we can say we're going to put things into our tree if the correct if all computations, struggling with this sentence again, we're going to put a node on this tree if all computations with hold in the number of steps bounded by the length of this node show that it's correct. Right? So this is the tree. Sigma in 2 to the omega is in there if WE, length of sigma, is contained. I don't really know how to write it. In sigma, and WI of sigma intersect sigma is empty. Right? I'm now doing the same thing in reverse. Here I wrote sets and I was thinking about characteristic functions. Here I write finite approximations to characteristic functions and I'm thinking about sets. But pretend I gave a definition of the head of a sigma that corresponds to exactly what you know it should be, and then here's a real definition. Right? And this is exactly the right thing, because if an S is not separating, then there is a counterexample that is being separating. That counterexample takes a certain number of computational steps. initial segments of S that are longer than that are not in the tree. Therefore, S is not in the corresponding closed set. So this shows that the collection of reals separating two CE sets is obtained from the set of infinite paths through computable tree. So WEWI pairs EI that are disjoint give rise to the type of sets we were just studying in the compactness theory. And now we remember one more fact, and that is that there are effectively inseparable CE sets. Right? This is one of the observations we made about CE sets, that there are CE sets which you cannot separate from each other by a computable set. One of the examples I think we saw was let WE be the set of indices E such that phi E of E holds and is equal to 0, and WI be the set of indices E such that phi E of E holds and is equal to 1. And then if you put them in the right order, any characteristic function of a separating set gives you a quick contradiction. So there are effectively inseparable sets, therefore there is this pi01 class with no computable branch. Because every such branch is a separating set and no computable such thing exists. Okay, so that shows that this idea, if your code is non-empty, you have a branch which is computable from the holding problem, is at least not completely missing the point, right? You can't remove the oracle of the holding problem. You need something. Now, the next theorem is about showing that you don't need that much, right? You don't need all of the holding problem. This branch can be picked to be a low set. So this is called the low basis theorem. And your first reaction might be, well, I know what the basis is of a vector space and the basis of other things, and this clearly does not look like that. But another use of the word basis is like a nice collection of objects, such that whenever you study this, you can find one of the things in the basis in there, which is exactly what this is saying, right? The statement here says the set of functions computable or Turing reducible to the holding problem form a basis, and we're going to improve the basis to the low sets. So as to say, if I have C non-empty pi01, then there exists an F in C such that F is low. Right? What does this mean? F jump is Turing equivalent to 0 jump. Now to show that F jump is Turing equivalent to 0 jump, you need to show that 0 jump reduces to F jump and that F jump reduces to 0 jump. One of the two is no work, because 0 jump reduces to any jump. It's the smallest jump that you can possibly have, right? 0 reduces to anything, therefore 0 jump reduces to anything jump. So all we need to do is find an F such that F jump Turing reduces to 0 jump. That's F in C, right? This is our assignment. Find something in this particular closed set that doesn't jump too far. What do you do? Well, what you do is first figure out f jump Turing reduces to zero jump. What does it mean? Well, it means that any question of this form, right? A computation relative to the oracle f, we need to be able to decide if this holds using zero jump. But if there was no f there, then that would be exactly a zero jump question, but there is an oracle f. And we need to find an oracle f which doesn't make this question too hard to decide whether it holds or not. And now if you look at it, which I just gave you a moment for, then I think you'll find that there isn't an immediately obvious way to find such an f. But there is a good way to get at it anyway. So first of all, C is non-empty pi 0, 1, so this means C is of the form the set of infinite branches through a 3T, where the 3T is computable. It's non-empty. Well, non-empty means exactly that this tree is infinite. Right? Koenig's lemma says then there's a branch. So we have this infinite 3T. And now, what can we do? Right? We need to do this for every E, of course, but we'll just focus on one given fixed E for a moment, and if we can figure it out for one E, then we may hope that it gives rise to a strategy to do it for all E. So if you have a particular E like this, then we can look at this set, those sigma in T, such that phi of sigma of E of sigma many steps, length of sigma many steps of E diverges. This is a nice set which I can define, and you know there's a couple of things about it. Well, first of all, you notice that this is a nice computable requirement. So we start with a 3T which is computable, then we add a computable requirement to it. So this here is a computable tree. One more observation for it. If you diverge with using oracle sigma as length sigma many steps, then you also diverge for shorter oracles and fewer steps. So it is a tree and it is computable. So this is a computable subtree of T. Now why is this tree interesting? Because if I now take an infinite branch through this tree, if this were the tree and not T, so if this were the subtree we were looking at, then any infinite branch has the same answer to this question, namely you diverge. Because if you do converge, then you converge in finitely many steps, so there is finitely many oracle questions that are answered, and there's finitely many steps taken, we'll take a sufficiently long initial segment of f, which includes all the oracle questions and is long enough for the computation to hold, and then that is an initial segment which is not in this tree. Therefore, if this tree is an infinite subtree of t, then exchanging this tree for t gives you one where you know the answer to this question. Now, when can you do that? Well, you can do that if there are f through this tree. When are there f through this tree? Well, if it's infinite, or if the root node is extendable. Well, we just proved that zero jump can answer that question. It can tell you, given this tree t, whether or not this particular tree is infinite. And if it's infinite, then we can now keep on considering this tree. Right? Zero jump, we can go to that tree. If this tree is finite, that means that for all but finitely many nodes in T, this computation converges, which means that for every infinite branch through T, the answer is yes, it holds. Because for every infinite branch, at some point you've passed, right? If this tree is finite, then these nodes are of have maximum length. If you take a branch through this tree, then some initial segment of this branch is longer than the maximum length of the nodes in this tree, and that is an initial segment which is enough to compute this, and therefore it computes it from the holding problem. So, what did I just show? I just showed that we have a zero jump computable question, is this tree infinite or not? And once we know the answer to that question, we either stick with T or we move to that tree, and that means that we've decided this one instance of the jump problem. Okay. But now, of course, well, we are essentially done. Because if I can do this for using zero jump for one given E, then I can also do it once after the other for different E's. I can start asking this question for 0. Is phi f of 0, does it hold or not? Right? Is this tree infinite or not? And then if yes, then I move to this tree. If no, I stick with this tree. Then I still have a possibly smaller infinite computable tree, which I can now use as the input for deciding phi f of 1, 1. And I can ask the same question again. And so, what did I just build? I built a sequence of trees which is decreasing such that...
Well, what did I achieve?
These TE are decreasing. I have that every TE is not empty, right? I use zero jump to decide, is this one tree infinite? If yes, I move to that infinite tree. An infinite tree has a branch through it, therefore the associated closed set is not empty. Otherwise, I stick with the already known infinite tree I had, which is therefore still infinite, and also has a branch through it. So I have these sets, these closed, non-empty sets TE, where the trees do this. But if the trees do this, then the closed sets are decreasing. But any infinite branch through this tree is also an infinite branch through that tree, so the closed sets are decreasing. Zero jump can tell me what the answer is to the halting problem of any f through the tree TE. Right? For any given E, zero jump can do the first E many steps of this construction and decide which way we went with the tree. Therefore, zero jump can decide what the answer is to the halting problem for any of these halting questions if I look at this set. Right? If I have an f in the intersection of these closed sets, zero jump. Right? Finding this f can be difficult, but zero jump can tell me how the construction of these TEs went, therefore what the answer is to these particular halting problems, so zero jump can decide the halting problem relative to this f. So the only remaining question then is, are there such f? And the answer is yes. Right? Why is the answer yes? One of the reasons why we care so much about counter space being compact. We are in a compact space. We have a nested decreasing sequence of non-empty closed sets in a compact space. Then their intersection is non-empty. So there is such an f. Notice that I possibly have not even decided whether f of 0 is 0 or 1. Right? I might not have decided that at all. But there exists such an f, and as soon as I have such an f, zero jump decides the halting problem relative to it. Therefore, each such f is low. There exists such f, each such f is low. We're done. Questions?
So the reason zero jump can decide the halting problem with f as an oracle is just because it only needs to go out to E to decide.
It just, right? I give it such an f. Now I say, what is phi f of E? Does it hold or not? Well, I just say, whatever. I start with my t. I do the first E steps of this construction. And I look at what is the answer by the time I get to the each step. Did I switch to this one, or did I stick with T? And if I stuck with it, then the answer is yes, it holds. If I switched, then the answer is no, it doesn't hold.